So last week, and the week before that, we had an introduction to the module. We talked about what are signals. We did a brief review of complex numbers and how we can use the phasor notation and uh, the impedances to analyze circuits. This week, if you haven't attended the last 2 weeks, it's a completely different topic, which we will start on, which is Laplace transform. Okay, so in today's class, we're going to look at what is the definition, what is Laplace transform, what does it mean mathematically, what are the properties of this transform, and then we're going to look at how we can calculate it forward and inverse. Then, so the first half of the lecture will be pure mathematics. The second half of the lecture will be how do we implement Laplace transform to analyze circuits. Is it clear so far? Are we good? So let's start with the definition. Laplace transform. Do you know what the word transform means? Transform something means to change it, right? From one situation to another, right? Laplace transform is to take a signal which is in time domain, and when I say in time domain, it means f of t. The independent variable is time. Whether it's a current or a voltage or an impedance, it's a function of time. When time changes, the value changes. So the Laplace transform transforms the signal from a time domain representation to a Laplace domain, which is a frequency domain. What does that mean? Just to give you a quick review of the time frequency duality of signal. If this is time and this is a signal, we can say that this is a cosine omega t plus theta, right? Where the value of this peak is a, the phase shift is the time between its start and its actual zero, and this omega is 2 pi over t, where t is one full cycle. You remember that? We discussed that time, t, the cycle, is another way to represent omega, the angular frequency, right? So even though mathematically here, this is basically f of t, a function of time, it can also be represented as a function of frequency, right? How many frequencies does this signal have? The frequency is 2 pi over t. How many times? Do you have different cycles? It's the same repetition, right? So it has a single frequency. It's operating in one frequency, right? So we can also plot it in frequency domain and say, well, in omega, this is my signal, or this is omega naught. Make sense? So you can visually see it as a function of time, which is a sinusoidal function, or as a signal that appears at one frequency. So generally, all signals or AC signals have what we call time frequency duality. I mean, it has time domain representation, it has frequency domain representation. Both give you the exact same information. Are you clear on that? So visually, this is how we see it. Now, mathematically, how do I express it? This is time domain. A cosine omega t plus phi is time domain, f of t, right? If I want to express it in frequency domain, or in what we will call today Laplace domain, Laplace is the name of the scientist who came up with this approach, we can call it f of s. So any signal can exist in time domain and in frequency domain. It's just the way you look at it. You look at it here with the perspective of time. The other way you look at it with the perspective of frequency. Make sense? So for any signal, sorry, for any signal, let's remove this. For any signal f of t, it has a pair f of. How do I get from f of t to f of s? By applying what we call the Laplace transform. So we transform it from t to s. S is equal to what? J omega, where omega is frequency. So S is a representation of frequency. So instead of being a function of t, it becomes a function of j omega. Are we clear with that? How do we perform the Laplace transform? By applying the integration. If you take f of t multiplied by an exponential e power st, negative st, then integrate this from 0 to infinity, you'll end up with f of s. So far, is it clear? Don't get scared by the integration. We will not integrate anything today. We'll have a table. So up to this point, are we good? Laplace transform is when you take a signal, which is in time domain, convert it to its representation in frequency domain. All good? Online, are we clear? So now let's move on to the inverse transform. Let's say that we accepted that each signal can exist either as f of t or f of s. If we start with f of t, we perform the integration that I showed you earlier, we end up with f of s. If we have f of s, we can do the inverse process to get back to f of t. Are we clear with that so far? Okay. And we call that the inverse transform. Now, here are the common functions. As I told you, today we'll not do an integration. We'll just look at the tables. These are common functions. Remember last week we talked about common functions like a sinusoid, a square, an exponential. So delta, do you remember what delta is? The unit impulse. The unit impulse is a function in time which has a single value at t equals 0, which is equal to 1. And the transform of f of t, where f of t is equal to delta, is equal to 1. And then we have the unit step, which is this function. At t equals 0 and above it's 1, at t less than 0 it's 0. The Laplace transform of the unit step is 1 over s. The Laplace transform of an exponential, if the exponential is e power minus at, is 1 over s plus at. So how do I get to this? By performing this integral. If you actually integrate, these are the values that you'll end up with. I don't want to overcomplicate it today. Let's just look at the table. So are we clear so far? Okay. Let's keep that in mind. And by the way, this table is very important because it will simplify for us. We will not have to do the integration. We'll just have to look at the table of the common functions, Laplace transform. So we call these the transform pairs. For every f of t, there is an f of s value. And if you know f of s, you can use the table to find out what was your original f of t, right? Now, if you notice, I gave you a formula for f of s. So if you have any function that is not on the table, then we have to integrate and we can simply find what is f of s, right? However, for the inverse, there is no formula, which means if it's not on the table, you have to make it look like something on the table. You have to manipulate it so that you'll be able to find the inverse of it. Is the concept clear? Now, this is purely mathematics, and I will show you in a moment how does that link to circuit analysis. So this Laplace transform has properties. These properties help you also simplify your calculation. For example, time scaling. So what does time scaling mean? This is a signal that starts from 1 to 2. I can scale it, so it starts from 0 to 4. What did I do now? Expanded it, right? Or we can shrink it. So it can start from 1.5 to 1.8, for example, right? So signals can be scaled in time. So if this is f of, let me use other values just to make it even more clear. Let's say from 0 to 2, from 0 to 4, from 0 to 1. This is f of t, right? This is f of 2t, right? This is f of t over 2, right? So I either shrunk it in time or I expanded it in time. We call this time scaling. So the concept of time scaling property of Laplace transform is that if you have a time scale function, but you knew the original pair, so you know that for this f of t, the Laplace transform is f of s. And then I gave you f of a t, a scaled value. All you have to do is you don't have to go back and integrate. Look at f of s, replace every s by s over a, and divide the entire formula by 1 over a. Make sense? We'll have an example. Another property is time shifting. So what does time shifting mean? This starts from 0 to 1. This is f of t. Time shifting means instead of f of t, you'll have f of t plus 1, which means instead of starting at 0, start at 1. You shifted it in time. Or you can have f of t minus 1. To start from minus 1 to 0. Make sense? So this is called time shifting. And if you have a shifted version of your original function, and you know the pair that f of t is the original function, f of s is the original transform, then any time shift, any shift in time, so if you have f of t and f of s as your original pair, then any shifted version, f of t minus t naught, will give you the same f of s, but multiplied by a factor e minus t naught s. Make sense? So a shift in time domain is equivalent to a multiplication by an exponential function in frequency domain. I'm just giving you the information now, but we'll practice on them in a minute. Because you need to understand. Are we clear? Similarly, there is the frequency shift. So if you have a multiplication by an exponential in time, similar to what we have here, then that results in a shift in frequency domain. So if you notice, if you shift in time, you multiply frequency. If you multiply in time, you shift in frequency. Make sense? So these are some of the basic properties of the Laplace transform. There are other properties which are listed here. There are about 10 or more properties of Laplace transform, and the whole purpose of the properties is what? Instead of having to go back and integrate and find the transform by integrating the function, if you know the original pair, you apply the property and you reduce your calculation. For example, if I ask you to find the Laplace transform of e multiplied by alpha t times cosine omega t. Now, the cosine, the tables will be in the exam formula sheet, but you need to know how to use them. Okay? This module is more on understanding, less on memorizing, because every equation you have will be in the formula sheet. Okay? So let's look at this. Exponential e power alpha t times cosine omega t. So I'm going to go to the table. Do we have anything on the table that will help us? Look. We have, okay, and cosine. You have cosine? You have the cosine. Okay, but our function is not e and cosine, it's e multiplied by cosine. And on the table, we don't have, actually we have it, but it's a property. So you have cosine is equal to what? Cosine bt transform is s over s squared plus b squared, where b is this factor multiplied by t, right? So if I go back to my example, cosine omega t, I know that if f of t is equal to cosine omega t, then the Laplace transform f of s is equal to what? Then the Laplace transform f of s is equal to s over omega squared plus s squared, right? Which is exactly what we have here. The number multiplied by t in our example is omega, right? And then it's multiplied by an exponential function, right? And when we multiply, it will not be correct to just multiply the Laplace of the exponential by the Laplace of the cosine. This is not mathematically accurate. However, we do have a property, just this one. If you have a function multiplied by an exponential, then what happens to your transform? It becomes what? F of s plus a, right? Let's copy this property. Copy it. So if this is your f of t and f of s there, so this is f of t, this is f of s. This is the pair, right? So cosine omega t has the Laplace transform of s over omega squared plus s squared. This is from the table. Up to this point, are you clear? Then, what would be the Laplace of e power alpha t cosine omega t, which is basically an exponential multiplied by my function? Then the Laplace transform of this case will be f of s plus a, which means replace every s by s plus a. Will be s plus a divided by omega squared plus s plus alpha is our factor squared. Make sense? Okay, we'll repeat one more time. We said that إن الجزء الأول واضح معنا إنه الترانسفورم الكوسين عبارة عن اس على اوميجا سكوير بلس اس سكوير، صح؟ طيب قانون الفريكونسي أو الفيز شيفت، الفريكونسي شيفت، إنه إذا في التايم دومين إذا عندك فانكشن اف اوف تي ضربنا الاف اوف تي في اكسبوننشال، ما يقابله في الفريكونسي إنه بدل كل اس هنعمل اس بلس اي كأن عملنا شيفت. احنا هنا ضاربين في اكسبوننشال، صح؟ إذا هنا بدل كل s this s and this s أو replace them s plus what قيمة الشيفت هي القيمة المضروبة في t في الاكسبوننشال، يعني هنا ألفا. أوكي، تبقى بدل s s plus ألفا في البسط، في المقام الأوميجا ما فيها s أوميجا سكوير as الحد الثاني the second term s squared becomes what s plus ألفا. Here which is what we have here. Similarly all the other properties, so whenever you have a property, either a time shift, a frequency shift, time scaling, or any of the properties on this table, you don't have to go back and calculate or go back to the table and try to match. If you have the original pairs, عندك الدوال الأساسية f of t و f of s, so what is the manipulation you have to do as per the rule. Another property is called the differentiation theorem, and this is very important for us. Okay, because it's available. This will be recorded and uploaded in Moodle. This will be in Moodle, inshallah. Okay. Fine. Now let's look at okay. Differentiation theorem اللي هو okay احنا we said we have properties, and if you look at the properties you'll notice that every property corresponds to a manipulation. يعني أي property عبارة عن أي تغيير بسيط يحصل في الدالة الأساسية ينتج عنه تغيير بسيط في اللابلاس ترانسفورم. فكان عندنا التايم shifting, shift in time, time scaling, frequency shifting, division by value, division by t, multiplication by t. يعني أي function we do something different to it. What if we have f of t, but instead of being multiplied or shifted, it's differentiated. عندنا المشتقة الأولى ال f of t. Similarly, the Laplace transform of d over dt of f of t, يعني المشتقة الأولى ال f of t, is equal to f ضرب f of s ناقص f of 0. Second derivative is المشتقة الثانية، القانون بيتغير. nth derivative, this is the general formula. Are we clear with that? Well, this applies to a lot of circuits because, as we explained last week, العلاقة بين الفولتج والكرنت في الريزستورز في الاندكتورز والكاباسيتورز is not always linear. Okay, you will see an example of that. Let's have another example. Let's start with this original pair. F of t is an exponential function. F of t is e power at. And this is f of s as per the table, which is here. This one. We have this pair. An exponential in time domain is equal to 1 over s plus a in frequency or in Laplace domain. What is the transform of the derivative of this function? مشتقة الإكسبوننشال. What would it be? This is the rule. قاعدة إنه عندنا the original pair is t, f of t and f of s. And we have the derivative of f of t, then the f of s will be equal to what? S multiplied by f of s. So this is f of s. S multiplied by 1 over s plus a minus f of 0. f of 0 معناها قيمة الدالة عند تكون t صفر. لو ملاحظين f of t is small letter f. f of s is capital letter f, right? So this f refers to f in time or the f in frequency, f of s time, which means I'll go back to here and replace t by t equals 0. E power minus alpha 0. Clear? Which is equal to what? E power 0 is what? 1. S over S plus A. Clear? Makes sense? So this is a second example. Another theory that we have is called the initial value and final value theory. The theory states that if you have a function f of t, the limit of that function when t tends to 0 معناها قيمتها الأولى أول قيمة لها لما t تكون صغيرة جدا it's almost equal 0 is equal to what? To the limit of f of s when s goes to infinity. يعني القيمة الأولى في الزمن when t 0 بتساوي القيمة الأخيرة في ال frequency لما s تكون infinity. And that's why the limit of f of t when t is 0 is equal to s times f of s when s is infinity. Initial value in time is equal to the final value in frequency. And the opposite. The final value in time, limit لما t almost infinity, is equal to the initial value in frequency. Okay? Why do we need this? لما نحلل دوائر كهربائية عندنا حاجة اسمها steady state صح؟ Final value. A system, when you run a system, مثلا لما يكون عندك مصنع, you have a machine, initially it overshoots and then it stabilizes, right? When you run a car, when you run the engine, it starts with high. If you look at the gauge, it starts a little higher and then it stabilizes, right? You have an initial value, which is a little bit high, and then a final value, which is the stable value. Right? So this is why we use this theory in circuit analysis. Make sense? Okay. Finally, and hopefully, let me see. I have forward, inverse. Okay. Two more mathematical slides, and then we'll start with circuit analysis. Finally, we have what we call the poles and zeros. So what are poles and zeros? Last week, we discussed transfer functions. We said that any system or circuit is basically a box with elements inside, resistors, capacitors, inductors connected in any way or form. You feed it an input, whether that input is voltage or current, and it gives you an output, right? We said that every system has a gain. And we said that the gain of a system is basically its output divided by its input, right? This gain could be V out over V in or I out over I in, whatever the output is or the input is. If you divide output by input, you get the gain, right? Okay. So what if your input is a function? Because whatever, if it's voltage or if it's current, if it's an external supply source, it's function of time, right? So your input is a function of time. Your output is a function of time, right? Equivalently, you'll have a transfer function or Laplace transform where your input is a function of s and your output is a function of s, right? Which is something like this. A fraction, right? So your transfer function or your gain is a fraction. Output divided by input, right? Zeros are values of s that will cause this gain or this f of s to be equal to 0. قيم s اللي هتخلي الدالة كاملة تساوي صفر. طيب متى هتكون الدالة بصفر؟ متى بيكون الكسر قيمته بتساوي صفر؟ لا، إذا المقام صفر قسمة على صفر بتدي كمية غير محددة، صح؟ infinite undefined value. لكن إذا البسط صفر قيمة الدالة صفر، صح؟ إذا قيم s اللي هتخلي البسط صفر هتخلي الدالة صفر. These are called zeros of a system. So zeros of a system are values of s that will cause this entire transfer function to be equal to 0. Why is it important? If the gain is 0, what does that tell you about this system? That the output is what? إنه الأوتبوت صفر، صح؟ which tells you about efficiency. السيستم هيكون الأوتبوت بتاعه صفر، خارج صفر، صح؟ و S values قلنا إحنا ال S بتساوي إيه؟ S بتساوي J أوميجا، صح؟ فلما نقول قيم S اللي هتخلي البسط صفر، أنا تحديدا بقول قيم الترددات أو الأوميجا frequencies that will give me zero output, right? So when you become a design engineer, it's very important to know your zeros so you can avoid operating at these frequencies. Make sense? Okay? Similarly, we have what we call poles. What is poles? Poles are values that will lead the denominator مقام to be equal to 0. وزي ما ذكرنا إذا المقام صفر إذا we cannot really predict the output. It becomes unstable. And we also need to know frequencies that will lead your system to be unstable to avoid operating these frequencies. Make sense? So you need to know the poles and the zeros of any circuit that you design, which are basically the values of frequencies that will either give you a zero output or that will give you an unstable, undefined output. Make sense? So you can avoid them. And it's easy to find them because you'll take this equation, equate it to 0, and then solve for s. This will give you zeros. And then you'll take this equation in the numerator, equate it to 0, and then solve for s. This will give you s values for the zeros, for the poles. We call these poles as zeros. Finally, if I want to find the inverse transform. Now we've already established that the forward transform is a formula, and there is a table that can help you with common functions. If the function is not on the table, we go back and implement the formula. What about the inverse transform? If I know f of s and I need to find f of t, in that case, I have to match what I have to the table. So let's take an example. Learning by example is better. Let's say that I have this function, which is my f of s, and I need to find the value of f of t corresponding to it. What would it be? If you look at the table, let me quickly run through the table. We don't have anything that matches that, right? Nothing. But I do have this, and I do have this, and I do have this, right? S plus, right? So what I will do is I will do something called partial fractions. Are we familiar with partial fractions? here partial fractions بصورة جزيئية. طيب this is a large fraction right؟ كسر ضخم فيه عدد من العوامل right؟ We can say that this is basically A times B times C divided by X times Y times Z صح؟ تقريبا which is basically, let's write it here, A times B times C divided by X times Y times is equal to A over X times B over Y times C over Z, right? It is also equal to A1 over X plus A2 over Y plus AC over Z. If you look at the right hand side of the equation الطرف الأيمن كانت عندك ثلاثة كسور صغيرة وحدنا مقاماتها X Y Z A times Y times Z plus A2 times X Y plus A3 times Y. صح? You remember this? And this should be equal to this, right? However, these are simpler fractions أبسط. صح? So the whole purpose or the whole concept of partial fractions is that you simplify a complicated fraction into simpler fractions in the hope that they will be available in your table so you can easily convert. Make sense? So let's start with this example. How many terms do we have in the denominator? في المقام كم حد عندي؟ You have S, 4, right? I'm going to make an assumption that this was originally 4 smaller fractions, and then I'm going to find what their values were. So this is basically equal to sorry, K1 over S plus K2 over S plus 2 plus K3 over S plus 4. Give herself some. We can say that F is equal to 12 S plus 1 times S plus 3 by S plus 2 S plus 4 S plus is equal to K1 over S, K2 over S plus 2 plus K3 over S plus 4 plus K4 over S plus 5, where K1, K2, K3, K4 are constant values. طيب, now does any of these new fractions match a function that we already have existing on the table? 1 over S and 1 over S plus 2. We have this one and this one, right? Which we can say that the Laplace transform of f of s is equal to different colors, is basically this Laplace transform. Of this entire thing, right? For this first term, we said the transform of 1 over s is what? U of t. And transform of 1 over s plus a is minus at. So let's apply it here. This becomes what? K1 is a constant, so leave it as is. And the exponential of 1 over s is u of t plus K2 is a constant. The exponential of 1 over s plus 2 is e power minus 2 T. Third term will be what? K3. And the last term would be, yes, makes sense? Now this is a part here. This is not a complete answer because I didn't calculate K1, K2, K3, and K4. But just from doing that, now I know how I can use the table. What I need to do next is just calculate what are the values of K1, K2, K3, and K4 that will make this equation correct. So to calculate, we already خلاص. Now we know what is the transform. We just need to know these factors, the values. So all I have to do is use partial fractions approach, which is I have to find each element by element. K1. If I need to find K1, every step will be repetitive, by the way, from this point onward. If I need to find K1, it's a two-step process. Multiply the entire equation by the denominator of K1. نضرب المعادلة طرفي المعادلة الأيمن والأيسر بمقام K1. Then substitute value of S that will make every other term equal to 0 except for K1. طيب, let's do this. We'll multiply here by S, by S, by S, by S, and by S. The integrity of the equation is still intact. And whatever I did here, so it's still equal, right? Now we know that our Laplace transform exists from 0 or from minus infinity to all the way to infinity. Values of frequency. Even though negative frequencies are not real, but we can use them. And this equation should be true for any given value of S, right? So I'm going to choose the one value that will help me get rid of my other unknowns. So what value of S that will help you get rid of K2, K3, and K4? Keep in mind that these two cancel each other out. What do I have left? And these two cancel each other out. If S is 0, what will happen to the right hand side of the equation? If S is equal to 0, this will be 0, this will be 0, this will be 0, right? So the right hand side of the equation will only have K1. The left hand side of the equation will have what? 12, 0 plus 1, 0 plus 3, divided by 0 plus 2, 0 plus 4, 0 plus 5, right? يعني مكان كل S هنعوض بصفر, right? I did two things. I assumed I did two steps. Multiplied the entire equation by S and then let S equal 0. So this gave me a way to only evaluate K1, which is equal to what? 12 times 1 times 3 divided by 2 times 4, which is equal to what? 6. Here. Let's keep this here. K1 is equal to 36 over 40. And let's repeat the whole process to find K2, K3, and K4. And with repetition, it will be more clear. So I'm going to start with the same original. Okay, now let's try and find the value of K2. What would you do? Said it's a two-step process. Step 1, نضرب كل أطراف المعادلة بمقام K2. الخطوة الثانية نشوف قيمة هتخلي العامل اللي احنا ضربنا به ده صفر. Okay, so what do we multiply with? S plus 2. Okay, let's do it. Times S plus 2 times S plus 2 times S plus 2 times S plus 2 and here times S plus 2. This and this cancel each other. This and this cancel each other. Now what do I substitute S with؟ قيمة S اللي هتخلي K1 K3 and K4 يبقوا صفر. You're there. Positive or negative 2؟ Negative 2 صح؟ لأن احنا بنضرب في S plus 2. So if S plus 2 is minus S minus 2 plus 2, it's equal to 0. So let S equals negative 2. If S is equal to negative 2, this will go, this will go, will go, right? And the only remainder term in the right hand side of the equation is K2. And on the left hand side, what do I have? 12 times negative 2 plus 1 times negative 2 plus 3 divided by negative 2 times negative 2 plus 4 times negative 2 plus except which is equal to what? 12 times minus 2 plus 1 is minus 1. Minus 2 plus 1 is plus 3 is what? Divided by minus 2 times minus 2 plus 4 minus 2 plus 5 3. 12 times minus 1 times 1 is minus 12. Minus 2 times 2 times 3 is, therefore K2 is equal to, make sense? Can we repeat the exact same process for K3? So what do I do next? If I want to find multiply by S plus 4 and perfect. So I'll multiply both sides of the equation by S plus 4. These cancel each other out, these cancel each other out, and if S is equal to minus 4, this is 0, this is 0, this is 0. Which means that here we have only K3 left, and here what do I have on the left side of the equation? 12 times minus 3 divided by which is equal to what? 12 times minus 4 plus 1 is minus 4 plus 3 is divided by minus 4 plus 2 is and plus 5 is 1. So 12 times negative 3 times negative 1 is, and 4 minus 4 times minus 2 times 1 is, so K3 is 36 over 8. Finally, let's evaluate K4. How do we get K4?
equal 5 minus 5.
Try it. So we'll multiply every term by S plus 5. These two will cancel each other out, and then let S equals minus 5, sorry, which means that these three are zeros, which means that K4 is equal to 12 times, which is minus 4. And then minus 5 plus 3, which is minus 2. And then here we have what? Minus 5 times minus 5 plus minus 3 and minus 1, which is equal to 12 times minus 4 times minus 2 is, are you sure? 12 times 8 is 96 divided by 5 times 3 times minus 15. Double check. Divided by minus. See? Are we good so far? Okay. So now that we have, yeah, ايوه. لا شوف احنا افترضنا افتراض، احنا الافتراض انه انت عندك اربع كسور، المقامات واضحه من نفس مقام الكسر الاصلي، صح؟ اما البسط انت بتفترض انها اعداد مجهوله مجاهيل، ممكن تسميها اي اسم، تسميها اكس واي زد اي بي سي، المهم انها مجاهيل. المطلوب منك انك تعرف قيمه المجاهيل دي كم عشان جوابك يكون مكتمل. اوكي. طيب now that we've established the values of k1 k2 k3 k4, can I find the Laplace transform, the inverse transform? So I'm going to rewrite this now that we know the values. So this is equal to, so f of s is equal to 36 over 40 times 1 over s plus 1 over s plus 2 plus 36 over 8 1 over s plus 4 plus or minus, because the last one is negative, 96 over 15 1 over s plus, right? From here, let's implement Laplace transform to get f of t. What would f of t be equal to? We said constants remain as is. ما بنغير فيهم، صح؟ بنغير في المجاهيل. So this is 36 over 40. And the transform of 1 over s is, we need to go back to the table. I might just a moment. U of t. And when we have 1 over s plus a, it's an exponential. Okay? So let's a moment. Okay. U of t plus the exponential, or sorry, the transform of 1 over s plus 2 is perfect, plus 36 over 8, and the transform of 1 over s plus 4 is minus 96 over 15. Clear? Makes sense? Do you have any question up to this point? Okay. So now that we did the inverse transform, so up to this point, just to recap the first half of this session, we learned about what is Laplace, how we do the forward, what is the formula, and how can we use the table, what are the properties that we use to simplify, and how we do the inverse transform, right? We talked about poles and zeros, we talked about how we can use the differentiation rule and so on. So how do I use all of this math in circuit analysis? Remember, this whole module is about circuit analysis. Sometimes when you're dealing with a circuit analysis problem, you end up with complex equations in time domain. And sometimes if you convert the problem from time domain to frequency domain or Laplace domain, it becomes more simple. So usually this is where we implement Laplace transform. You have a problem in time domain, which is complex. So you do a three-step process. Step one, convert from time domain to Laplace domain. The problem becomes simple. You solve for your variable or for your unknown in frequency domain. You get your final answer in frequency domain and then you convert back to time domain to give your answer in time domain. Make sense? For example, let's say that I have this circuit. It's a resistor and an inductor connected in series. And the question is find the current in the circuit, ignoring initial conditions. So this is a very important information. And assuming that your voltage Vt is a constant DC voltage, Vt is equal to Ut. What does that mean? It means that your voltage is 1 volt, right? So the unit system is a function with value of 1. Does that make sense? So the question is find the current I passing through the circuit. Now, do you remember Kirchhoff law? Kirchhoff voltage law? What does it say? The algebraic sum of voltages in a closed circle is equal to 0. لو قانون حفظ الطاقة يعني if you start with something you lose it and then you end up with 0, right? Let's apply Kirchhoff law here. This is my source V. V of t is equal to what? V1 of t plus V2 of t. صح? All clear so far? What is V1 of t? V1 is the voltage across the inductor, right? The voltage across the inductor is equal to V L di over dt. Sorry, V is equal to L di over dt. Do you remember that from last lecture? This is the voltage across the inductor. لأن الvoltage across the inductor is a differential equation in current. With each changes in the current, the value is change. So this is V. And V2 is what? The voltage across the resistor. And the voltage across the resistor is equal to what? Think Ohm's law. Voltage across the resistor is equal to right? Voltage is I times R. You remember Ohm's law? I is V over R. R is V over I. V is I times R. Do you remember that? So applying Ohm's law, this is what we end up with, right? V is equal to R times I plus L di over dt, right? And this is V of t. And this is I of t, right? This is our problem in time domain. And we need to solve for I. The unknown is what? I. So what we need to solve for is I of t is equal to what? This is our problem. What is I of t? This is our problem, but it's in time domain and it's what? A differential equation, right? And if I try to isolate I in one side of the equation and V in one side of the equation, we can say that by dividing by L, di over dt plus R over L, I of t is equal to 1 over L, V of t, right? It's the exact same equation, just rearranged. This is our problem in time domain. And it's a differential equation, which is not the most direct equations to solve, right? So what we will do is we will convert our problem from time domain to Laplace domain in hope that it will become easy to solve. How do we do that? Term by term, we take each term and convert it by applying the inverse transform. What is the Laplace transform of di over dt? We had the differentiation theory, right? It says that the Laplace of a derivative is equal to what? F of s minus f of 0, right? So this is what I will apply here for the first term. So my function is called I of t, right? So the transform of di over dt is s I of s minus I of q, right? And then what is my second? Let me write it here to make it straightforward. Here, s I of s minus I of q. So this is the Laplace transform of the first term plus second term. L and R are constants. Constants are left alone. The transfer of I of t will become what? The transform of f of t is f of s. So the transform of I of t is I of equals to 1 over L is a constant. The transform of v of t is, if it's called I of f of t in time domain, it will be called f of s in frequency domain. Make sense? Are we clear so far? Any questions up to this point? Okay. Now can you solve? But before we can solve, there is one key information that we're given here. Ignore the initial, which means this term over here is ignored. Initial condition means the value of the variable or of the unknown when time is equal to 0. Right? So I have 0 is ignored. So now what I have or what I'm working with is si of s plus r over l I of s is equal to 1 over l v of s. Now can I solve for I? Can you isolate I and say that I is equal to so-and-so? How do we do that? From this left side of the equation, take I of s as a common factor. We have I of s times what? S plus f equal to 1 over L V of, and this means that I of s is equal to 1 over L V of s divided by s plus r over s, right? Which is equal to, let me get myself some extra space here. So this is the point we stopped at, that I of s is equal to 1 over L divided by s plus r over L V of, right? Any question up to this point? Here. Okay. So what would you do next? Mm, okay. But okay. Before we go there, do you have any other information that helps? Vt is equal to u of t, which means if Vt is equal to u of t, then Vs is equal to what? If Vt is u of t, that means Vs is 1 over s. 1 over s, which means that this here is actually what, right? Makes sense? Now, does this look something like something that we can find the inverse of? So we've already found what I of s is. We solved the problem in Laplace domain. So we did step 1, which we converted the problem from time to Laplace domain. We did step 2, which we solved for the current for I of s. We find what I of s is equal to in Laplace domain. Step 3 now is to go back to time domain, because what we need to find is actually I of t, not I of s. So now can we solve for this? Using what? Is there a table value that equals to this? So what we can do is say this is a partial fraction. with a over s and b over s plus r over, right? Which is the exact same thing we did in the previous example. Does that make sense, you know? And therefore, we can say that I of t will be equal to a u of s plus b e power minus r over l u of t first, right? From the table. Does that make sense to you? And all we have to do now is find the values of a and b as a function of r and l. Are we clear on that? Or a little bit? Okay, so here is the table. Where is it? Here. Oh no, that's not the table. But here's the table. Mm-hmm. Makes sense? So this is what we have here. This is here. Clear? Makes sense? So it is easier somewhat to solve the problem in the frequency domain. And this is why we need to use these types of transforms. Make sense? كيف الوضع؟ Okay. So we have here, just to make use of our time, I've already calculated the values, and this is what you end up with. A is equal to B equal to minus 1 over R, and this is our final transform. Clear? Now you'll notice in the second term we also multiplied by a u of t. Why? Good question. Because you go back here to the first slide here. What do you notice about the limits of integration? Where do they start and where do they end? Which means that realistically, because usually when we use Laplace transform, we use it to mathematically enhance our calculations, right? We are dealing with real circuits and real systems, and there is no such thing as negative time or negative frequency in these scenarios, right? So that's why when we solve, we always multiply. Where's my final answer? We always multiply by the unit step because the unit step automatically eliminates every negative value by multiplying it by 0. It only keeps positive values. And that's why you multiply by u of t. Here. So this is not a mathematical thing. This more is a physical thing for realistic values. Make sense? Any question up to this point? Okay, now if you look at this, circuit and you're asked to plot I of t, what would it look like? Try to plot it. I will show you in a moment. Just let me plot it. This is t, and this should be I of t. It would look like what? 1 over r times u of t is what? It's a constant line at height 1 over r, right? And the second term is, what am I doing? 1 over r times the decaying exponential, right? Which is basically looks like this. So this is 1 over r e power minus r over l t, right? And then if we are to add them together, this is what you end up with. 1 over r minus, because they are minus, right? 1 over r minus 1 over r is 0. And then we have a steady line that's gradually increasing, right? So this is what it will look like, correct? Now I'd like you to pay attention to two things here. You notice 1 over r u of t is a stable line. It doesn't change, right? And eventually, actually it doesn't look more realistic, eventually the exponential becomes 0, right? So eventually, the current maximum value that it would reach is 1 over r, right? So 1 over r is our steady state value, right? It's our final value. And then here we have what we call transient state, this gradual increase, right? Now if you notice this second term, 1 over r is a constant and it depends on the value of r. But if you look at e power minus r over L, r and L are components of the surface, right? And the value of r and L dictates how slow or fast this decrease happens, right? And therefore it dictates how slow or fast do we reach our final steady state. Make sense? So the component values and the way they are connected in the circuit dictate the transient behavior. Make sense? We call this, so we have two types of responses to a circuit. We have what we call the forced response and we have what we call the natural response. Now, do you remember what was the input to the circuit? What, what was the value of the input? U of t, right? And what is the final steady state value? A constant, right? Your input was a constant value. Your output is a constant value. So we call this the forced response. Make sense? Which means you have to follow whatever the input is. You cannot come up with something new, right? This transient behavior, the gradual increase, we call it the natural response. Why? Because it relies on the value of the components and the way they are connected. So if you change this to a parallel circuit, it will change. Make sense? So this is another way to judge your circuit performance. And when you become a design engineer, you get to choose the values for R and L to tell you how fast or slow your circuit will respond. Make sense? In a way? Okay. So I just jump to this. Now, generally, this leads us to the concept of generalized impedance. So last week we talked about impedance. We said that we have ZR, which is equal to R. Last week we studied that ZL is equal to J omega L, right? However, now we know that J omega is equal to what? S. So ZL in Laplace domain is equal to SL. We studied also that ZC is equal to 1 over J omega C, which is equal to 1 over S. So with that, we can easily simplify our Laplace transform processes. Make sense? Now, if you look at this circuit, some time, so time, okay. If you look at this circuit over here, can you find the transform function if your input was V1 and your output was V2? So what is the transform function? Transform, we said it's the output divided by the input, right? So it's V2 divided by V1, correct? Do you remember the voltage divider rule? So the current passing through here is I, right? Which is also the same current passing through the resistor, right? The total current is V1 over the total, right? And the current passing through R is V2 divided by R, right? If we take only these two terminals using Ohm's law, the voltage across the elements divided by the resistance of the element, which means if you cross multiply, your V2 over V1 is equal to ZR over the total. Make sense? No? No? So are we clear with this equation? what you'll do is you will do the same thing to both sides of the equation. Multiply by this total, multiply by this total, divide by V2, or sorry, no, divide by V1, multiply by R, multiply by R, divide by V1. These cancel each other out. V2 over V1 is equal to the R over the total. Okay? Now that we have this in mind, let's use the sum of S of S. ZR is equal to R. Z total is equal to ZR plus ZL, which is R plus SL, right? Yes? Now, can I find this in time domain? Can I find the V2 of T? If V1 of T is equal to U of T, similar to previous example. V2 of T is equal to R over R plus SL times V over not of T. Yes? We multiplied by V1 here. These cancel each other out, and that's what we have. Yes? And if V1 of T is U of T, that means V1 of S is equal to what? 1 over S. Okay? So this is very similar to what we did previously. Just want to show you 1 over S, right? Now, similarly, can I find V2 of T using partial fractions? Yeah? But first thing I need to remember is that I need this to be in the form of 1 over S plus a factor. Here we have S multiplied by L. I need to get rid of that L. So it can be S separate plus a factor, right? So to do that, all I have to do is, right? Which means that V2 of S is equal to R over L divided by S plus R over L times 1 over S, right? Which is equal to A over S plus V over S plus R over L, right? Which means that V2 of T will be equal to A U of T plus B e power minus R over LT U of T, right? Now ignore the values of A and B. If you look at this and compare it, now here we're evaluating the voltage V2, right? And in the first example, we evaluated the current. What do you notice? It's the exact same, right? Specifically, uh, sorry, specifically this second term, the natural response, right? So this is to tell you that, and this is that the natural response of a circuit remains the same regardless of what quantity you are measuring. Whether you're measuring voltage, you're measuring current, you're measuring voltage of a different element, the natural response will always be the same. It will always be dependent on the structure of the circuit and the value of its components. Make sense? Questions? So now we've covered natural and forced responses. Just to give you a summary of what we've covered today. Today we studied the concept of Laplace transform, the forward and inverse transform, the properties of Laplace transform that we can use to simplify calculations, and some of the theorem like the initial and value theorem and the differentiation theorem. And then we studied how we can use Laplace transform to solve circuit analysis problems by the three-step process, converting from time domain to Laplace domain, solving the problem in the Laplace domain, and then converting back using the inverse transform. Here, okay? So if you have any further reading interest, you can go. It's the same book from last. Actually, that's different. That's Erwin and Nels. This is also available for you in the library. If you go to chapter 13, you find more problems on Laplace transform. Any questions? And I will try to upload this week to you tutorials, additional. I've mentioned last week that I will add complex numbers and phasors, and then I will add also Laplace transform. Yes, just a moment. Let me just stop our recording and I will